In this video, I'll do a practice problem that's going to be based on NMR and IR. So suppose I'm given this formula, which is C6H12O, and I need to figure out what the structure is going to be out of that. And the very first thing I want to do anytime you're given in a formula is to find the DOU. So the degrees of unsaturation here, or the index of hydrogen deficiency, which is the IHD, so either one of those, are going to be here as 2 times the number of carbons, which is 6, plus 2 minus the number of hydrogens, which is 12, and divided by 2, you ignore oxygens, there's no halogens, there's no nitrogen in there. So this comes out to be 1 in here. So what that means is either I have 1 pi bond, which could means it's in a double bond, or I have 1 ring. I'm not going to have both of them together. I'm just going to have one or the other. Now, I don't know whether I have a pi bond or a ring just based on the DOU. It just kind of gives me an idea that this is what I'm going to have in there. So the next thing I need to do is to look at what my IR looks like. So remember, the IR primarily tells you what is going to be the function group. So starting from the left side, I do see I have some signals here that are right below 3000. So those are going to be your carbon hydrogen stretches, but that carbon is going to be in an sp3 carbon. That's all really got on there. Moving along to the right side, the next prominent signal I see, it's at 1700. That's a very intense peak, which tells you that it's going to be a carbonyl signal. So I don't want to worry about anything else beside that because anything below 1500, it's kind of hard to decode. So I want to focus more on from 4000 to 1500, which is the diagnostic region. So I know I have a carbonyl here, and that kind of clears it up because I do have 1 oxygen here, and that takes care of 1 DOU in there because I have to have a 1 pi bond in there. That would make a 1 DOU. So I have a carbonyl, and since it's only 1 oxygen, either I have an aldehyde, possibly, or I have a ketone. Now, do I have an aldehyde or ketone? You can actually tell that based on the IR, because for an aldehyde, your this stretch right there usually shows up around 2700 to 2800, 2850, somewhere around that. And it's usually a very significant, I would say, mild peak. I wouldn't really say super intense or very strong, but it's a mild peak that's something that you can't really ignore or you would not be able to ignore. I don't really see that anywhere down there, so that tells me that maybe I don't really have an aldehyde. But I wouldn't really bet on this because I want to kind of confirm it somewhere else as well. In addition to the IR signal for this aldehyde, that hydrogen of that aldehyde actually is supposed to show up in the proton NMR anywhere between 9 to 10 ppm. And maybe I want to kind of go ahead and look at the proton NMR as well, just to kind of clarify whether or not I have an aldehyde. So when I look at the proton NMR here, so my proton NMR is this one here, and it kind of goes only up to roughly 3-ish here, or almost like 3.5, 2.5, which means I probably didn't have any signal down there. So that's why they didn't really put anything down there. So that means I don't really have anything at around 9 and 10. So that tells me that this cannot be an aldehyde. It has to be in a ketone. Okay, so that kind of gives it away that I have a ketone here, and this is a signal in IR that I can almost bet on that it's in a carbonyl. So that makes it an ketone. Now, what type of ketone? So I got 6 carbons. Let's see what other proof I can get. Now, I know I have a proton NMR, but I also given a carbon NMR. And if you're given a carbon NMR, I want to kind of see how many unique signals I have in the carbon NMR. So I see here that I get 1, 2, 3, 4, 5, and 6 signals. And remember, this is in a CdCl3. That's your solvent, so ignore that one. So I got 6 signals. So that means I got 6 unique carbons. So how many carbons do I have actually? I have 6 carbons. So that means all those carbons are going to be unique to one another, or they're going to be chemically different from one another. That's why you're seeing the different signals for those. And another thing I want to kind of mention here, this signal right there around, what is it, 210-ish? That's in a carbonyl signal. Remember, your ketone and aldehyde shows up anywhere between a 190 to 210. So that kind of confirms it again that you're going to have either an aldehyde or a ketone. This would not confirm it that you would have an aldehyde or ketone just based on the carbon NMR, but we ruled out the possibility of the aldehyde based on the IR and the proton NMR. So this has to be in a ketone. So I have 6 unique carbons in there, and I'm also given depth 135. So in the depth 135, remember your CH3s and the CHs are positive, so that means this gotta be either the CH3 or CH, and this gotta be either CH3 or CH. And then the one that are negative, they are gonna be CH2. That's in a CH2, that's in a CH2, that's in a CH2. Now, the depth of 90 is supposed to be showing the CHs, so I don't have no signal in depth 90, so that means there is no CHs in there. So all these are going to be the CH3. So based on that, I can say that, oops, come on, that this would not be this, and that would not be this. So it's just going to be CH3s and the CH2s. So I have 3 CH2s, 2 CH3s, and one of them is just going to be carbonyl. So if I want to go ahead and lay those out and put those together in here, I have 6 carbons, so I want to go ahead and put them in a simple long chain here. And one possibility is that I have a carbonyl right in the middle, right here. And another possibility would have been I have a carbonyl right here. So those are the 2 possibilities I have. And the question would be, which one I'm really looking at here? Is it going to be this or that? And because both of those would actually give you 6 signals. We got 1, 2, 3, 4, 5, 6. Because I don't really see an internal plane of symmetry in there. Because, you know, if you draw the line vertical here, the right side only has 2 carbons and the left side has 3 carbons. Same story here, there's no internal plane of symmetry in there. And the number of carbons and the number of signals are going to be the same in both of them. Because that would be, let's say, carbon 1, 2, 3, 4, 5, and 6. Say the same thing, 1, 2, 3, 4, 5, and 6. So the carbon NMR may not be able to tell you whether I have this one or that one. I mean, it does tell us that, okay, I got all these carbons to be unique to one another, and it does tell you that I have 3 CH2s. But in both of those proposed structures, like carbon 2 here, carbon 3 here, carbon 5 here, they're all CH2s. Carbon 1 here and carbon 6 here is going to be your CH3s. And even in the second structure, I have 3, 4, 5. They are going to be your CH2s. So same number of CH2s. And 1 and 6, again, going to be the CH3s. And you have the carbonyl in each one of them. That's going to be around 210. So the carbon NMR alone would not be able to tell you whether I have this or I have this. And that's when I go to the proton NMR, because proton NMR should be able to tell me actually the skeletons in there. So let's look at what the multiplicities are in the proton NMR. This is a triplet, all right? That means, okay, so that's a triplet. Let's look at what else. This is a singlet, so that means this signal has no neighbor, no hydrogen atoms adjacent. This is another triplet. So if I want to look at, do I have any proton in between those 2 structures where I do not have any neighbor or neighbors protons? And if I look at, suppose if I look at this carbon 1 here, carbon 1, which is going to be CH3, so there's 3 protons, actually has 2 neighbors, 2 protons neighbors on the second carbon. And I can say the same thing, okay, this proton here would have two neighbors, one on the left, one on the right. I can say something similar. The proton on carbon 3 here would have two neighbors on the left side, and then carbon 5 would have three neighbors on the 6 here, because 6 is CH3. And the proton on carbon 6 has two neighbors on carbon 5. So these are all going to be having some sort of adjacent hydrogen atoms. So none of those protons would show up as in a singlet. So I would rule this structure out for that reason. So always kind of look for a signal that you can almost bet on and not kind of get confused or too dangled in with multiple peaks in there. You want to be able to kind of justify the rest of the peaks as well, but just kind of start focusing on one of them first. Now, when I'm looking at this second one, the second structure does have a CH3 that's on carbon 1, and it does not have any neighboring protons because carbon 2 actually does not have any hydrogen atoms. So this CH3 should be showing up as just in a singlet. So I can say that this should be your carbon 1 protons on there. Those going to be your 3 hydrogens on carbon 1. And then I can justify the rest of them. Carbon 6, all right, so carbon 6 I got here is in a CH3, and how many neighbors it has? It has two neighbors on carbon 5. So that three hydrogens here would show up as a triplet. And I do have the triplet here, and this should be actually the most shielded out of all of them because this is furthest away from the carbonyl. So this right here should be this guy right there. So I would say this is going to be 6 here, and then I can justify the rest of them. I would say this carbon 3 or the protons on carbon 3 are going to be the most deshielded. They're going to be more deshielded than the CH3s on carbon 1 because they are actually the CH2. The CH2 itself is more deshielded than the CH3, and they're both are actually at an equal distance from the carbonyl. So this proton signal on carbon 3, which is two hydrogens, all right, so I got two hydrogen atoms, and how would that show up as? That would have two neighbors here, two hydrogen atoms, neighbors on carbon 4. That would be actually a triplet. Oops, ooh, what happened there? Sorry about that. That would have two hydrogen atoms on the neighbor, so this should show up as a triplet. So I do have a triplet right here, so this is going to be the protons on carbon 3 here. And then I can justify the other one as well. So carbon 4 is going to be next one in terms of deshielded because between carbon 4 and carbon 4 would be more deshielded than carbon 5. But how many neighbors carbon 4 has? So carbon 4 has two neighbors on the left side and they got two neighbors on the right side. So these two protons on carbon 4, they would show up as in a pentate if the coupling constants for the left neighbors and the right neighbors are the same, then you can say exactly it's going to show up as an pentate. But if they were not the same, they would show up as like in a multipentate. So I do have technically 1, 2, 3, 4, 5. So it's in a pentate right there. So this would be 4, and this leaves it with 5. And just see how many signals I got here. 1, 2, 3, 4, 5, and 6. So it must have 5 neighbors, assuming all the coupling constants between the neighbors would be the same. So proton 5 has 3 neighbors on the right side, and proton 5 has 2 neighbors on the left side on this carbon 4. So I do have a total of 5 neighbors, so that would give you in a sextet here or 6 peaks in there, and that's what you're really getting in there. And that would happen only if the coupling constant between 5 and 6 and 5 and 4 are actually the same. If their coupling constants were not the same, I would not be able to see in a clean sextet here, but rather in that case, it would have been either a triplet of quartet or quartet of triplet, or a better way of saying it would be in a multipetet in that case. So sometimes, like you can see here, how you want to approach this, you want to start with finding the DOU, finding whether you're going to have a pi or ring, or how many pi bonds, how many rings possibilities. From the IR, figure out what functional groups you have. and then you start kind of narrowing down by looking at the proton NMR and the carbon NMR. If you're given the carbon NMR, I would probably look at the carbon NMR first because that would tell you how many distinct type of carbons you're going to have. But then you may not be able to kind of decode the structures based on just one of the spectrums only. You may have to use a combination. Like I was not able to decode whether I'm going to have this one or this one just based on the carbon NMR. Now, if I knew their literature values of their chemical shifts exactly, then maybe, but we don't really know those. We just kind of go qualitatively more on shielding versus deshielding. So carbon NMR alone wasn't really able to determine that, okay, I'm going to have this structure as my final structure, and that's why we have to take the help of proton NMR in there.